So in this differential equation model or problem, we're being told that we have 200 fish at the beginning of the event, and we're going to be harvesting some number of fish per year. We don't know what that is yet, but some quantity B, where B is a positive number. The population is modeled by the differential equation, so that's nice that they've given that to us here. And again, at the beginning of the event, we have 200 fish. So find the fish population in terms of some harvesting rate B. All right, so this is basically us just solving the differential equation. So I'm going to write this as dy dt equals 0.2y minus b, where b is going to be some number, but we don't know what it is. So I'm going to treat it like a number, even though it's some constant. So if I recall, the trouble that we have with separating these differentials is we should probably have some sort of GCF or some sort of common factor so that we have a product of two terms rather than just the sum or difference of two terms. So I'm going to treat 0.2 as that GCF. I'm going to divide both of these by 0.2. And so now we have y minus some quantity b divided by 0.2. Now I can divide and separate the y components to the left side. I can bring the t components to the right with the other coefficients or constants, and we can proceed from there. So I now have 1 over y minus b over 0.2 dy equal to 0.2 dt. Integrate both sides of the equation, and we have the familiar natural log of absolute value. Now the coefficient in front of the y is just 1, so we don't have to do any obtrusive chain rule or anything to fix that there. So this is good as the antiderivative. The c value that would show up here, I'm already going to push over to the right side. And so now we have our 0.2t plus c. Use an exponential to eliminate the logarithm. So now we have y minus b over 0.2 equal to c times e to the 0.2t. Add this term back to the right, and now y, our fish population, is equal to our initial value c times e to the 0.2t plus b over 0.2. Okay, cool. So if we're supplied the b value and the c value and the t value, we can finally figure out what our final population for the fish will be. Now, it is worth noting that in general, anytime that we have a derivative equal to, whoops, this should be ky, there we go. So in general, if the derivative is equal to some constant multiplier of the original function plus some additional starting or harvest rate, if you want to call it that, some additional constant, in general, the solution ends up being in this format here, ce to the kt minus b divided by k. And so in this particular problem, if, let's see here, our k was equal to 0.2, our b value is still unknown, but if we let k be 0.2, and I got to be careful here. Oh, but we had a negative b up here, so b is negative b. I was wondering why we were getting the minus sign here. In our example, we came out with positive because our original problem was a negative b. So that negative b changed the sign here. So in general, if you wanted to take a shortcut, if you had this memorized, a differential of this form always turns into an original initial value solution in this form. So anyway, moving on from here, I think it would be a good idea to find our c value for the initial case. We know that there were 200 fish at the beginning when time was equal to 0. So we have 200 fish equal to some c e to the 0.2 times 0 plus some b divided by 0.2. We can isolate c now in terms of b. So this is all equal to 1. Then 200 minus whatever b over 0.2 is going to give me my c value. So it doesn't look great at this point, but it is manageable, I'd say. The total population for the fish is going to be equal to our c value, which we're now saying is 200 minus our b divided by 0.2 times e to the 0.2 t power plus b divided by 0.2. And there we go. There's our expression that we can use moving forward. So interestingly, in part B, I'm not going to worry about graphing it here. I think you would choose the graph on Math Excel, the one that fits the best. But interestingly, we're saying that we're going to harvest 20 fish per year. So if we evaluate this function at 20, so 200 minus 20 over 0.2, e to the 0.2 plus 20 over 0.2. And does it give us a time? No, it just says in general. So if we were to harvest 20 fish per year, then we'd be able to look at a graph when this is simplified. Now 20 divided by 0.2 is the same as 20 times 5, so that's 100. So 200 minus 100 is 100, e to the 0.2 t power plus 100. I'm not graphing this, but I know what this is going to look like. This is going to be some sort of exponential growth curve that has a horizontal asymptote at 100 and then races upward towards infinity because we have the positive leading coefficient along with a positive growth factor here. So I know that's the shape. This is generally what's going to happen. If we only harvest 20 fish per year, we're safe. We have enough in the population and we're not taking too much out for us to hurt our overall population. We can't say the same though in part C, because in part C I think we're harvesting something different. We're harvesting 120 fish a year. So this is now 120 over 0.2 times e to the 0.2 t power plus 120 over 0.2. Now here again, to divide by 0.2, that's the same as multiplying by 5. 120 times 5, I believe, is 600. So 200 minus 600 is now negative 400 e to the 0.2 t power, and then 120 divided by 0.2 is positive 400. So in this case, the shape of the graph would look something like this. We have a horizontal asymptote at 400, and because we have a negative 400 multiplying by an exponential growth function, this will be an exponential growth function, but one that's on the decline. So we'll see our population do something like this. So the two shapes are radically different. Obviously, we don't want our fish population to disappear altogether unless we were trying to eliminate the fish population. We would probably like to see our population grow, but we don't want it to get out of hand. So the question, I know it's not asked here, but the question might be, well, what's it going to take to maintain this steady state or maintain this equilibrium status? So I lost part of that recording there, but essentially what we're going after, or what we could go after next, is finding out the b value that maintains a constant population. So evidently with b being 20, our population raced towards infinity. With b being 120, it raced towards negative infinity. Is there a quantity between 20 and 120 that allows us to maintain that constant population? So I'm going to let you think about that on your own. Come back to me with some solutions or send me a message and we can chat about it some more. And we'll probably revisit this on Tuesday when we see each other next in preparation for the exam. Thanks for watching.